Let's consider the function f of x equals x raised to the x when x is bigger than 0. And let's find any minimums or maximums. This is fairly vague, so at the end, after I found out where there might be local mins and maxes, thinking about the first derivative test, let's go through and see if we actually have absolute mins or absolute maxes. So I have a function, y equals x raised to the x. Function raised to the function, and I need to take a derivative. This is where I like to use logarithmic differentiation, because I get to rewrite that exponent as a product. So now I can implicitly differentiate both sides using the product rule. This is actually an example we used for logarithmic differentiation in our last unit of study. So I'm just going to go through and differentiate. On this side, I need to use the product rule. And I find out that the first derivative, y prime, is, well, y, so x to the x, times 1 plus the natural log of x. I need to find any critical points, and so I'm looking for where this derivative is either undefined or equal to 0. And a positive to a positive, because x is always positive, is always defined. The natural log of a positive number is always defined. So I'm just looking for values where the first derivative might be equal to 0. Well, because x is positive, x to the x is in fact always positive, so I just need to worry about setting the second part equal to 0. So the natural log of x is equal to minus 1 when solving this equation. Rewriting that as an exponential, I would have x is equal to the base e raised to the minus first. So 1 over e is my only critical point. So when I look at my first derivative number line, all of my x's are bigger than 0. 1 over e is my critical point. And I just need to know whether my first derivative is positive or negative on these two intervals. And so pause the video here and use the first derivative. Pick a value in this region and a value in this region and see if you can tell, fill in these blanks for a positive and a minus. All right, you can pick any value you wanted to that's less than 1 over e, so maybe you thought to yourself that knowing an approximation for 1 over e would be helpful. So 1 over, well, let's just say e to the minus first is about 0.36. So you can plug in anything you want. Maybe you said 0.3, maybe you said something like 0.1 because you thought it would be easier, but whatever what you chose in this interval, when you plugged it into your derivative, you found out that you got a negative. On this interval, you could have picked anything bigger than 0.367879 that you found. I like to say e is bigger than 1 over e, because when I plug that in there, I get e to the e times 2, which is assuredly positive. So I know my function decreases and then increases, which would tell me that at least f of x equals x to the x has a local minimum of some number we need to write down at x equals 1 over e. Well, x raised to the x, this is 1 over e to the 1 over e. Not a very pretty number, but we can get a decimal approximation for it. And in fact, I have my calculator already set up with x raised to the x power n for y equals x. So if I come over to the table and I put in 1 over e, or e to the minus first, I find out that the y value is about 0.6922. And I'll just round it to 4 decimal places because that's what my calculator gave me. So, I don't know, let's think about this. I can't plug 0 into the function x to the x, but everywhere else, I get a positive number. When I plug in a positive to a positive, I get a positive. So my function starts, I don't know, maybe at some y value goes down and then back up. Let's look at the graph on our calculator, because I think this is actually an absolute minimum. And so I've zoomed in. I'm using a window here where the x-axis starts at 0 and the x-axis ends at 3. The tick marks are every 1 unit, and on the y-axis I'm starting at 0, ending at 4, and the tick marks are every 1 unit. And this is x raised to the x power, and I see the lowest point there. That would occur when x is 1 over e, and apparently at about 0.6922. And it goes down and then up forever, and it does behave as if that is an absolute minimum value.